All right, guys. We're gonna get started. All right. Once again, thanks for taking the time to come to lecture. I know you guys are all very busy, so once again, really appreciate this. So before we get started, I just want to do a quick introduction. My name is Rafi. I'm the education project lead here at ML at UVA. By the way, in case you guys are confused, we're no longer SIG-AI. Yay. We are ML at UVA. So some rebranding. Thanks for our president. So if you haven't done so already, please make sure you complete these the first two QR codes. Everything we do is on Discord, all communications, make sure you're in there. Engagement survey, that's how we kind of track our members. If you haven't really completed the engagement survey, like we don't really know that you're part of the club, right? So if you want to do any project with us in the future, host a reading group, like really engage with us, you have to be on the survey. So shouldn't take more than 5 minutes, 10 if you're writing a paragraph. That's not needed. And then finally, we're going to be starting interest projects or IPs, and we'll go more on this next week. But for those of you that want to get started early, interest projects are where you guys can kind of come to us with just budding interest and, hey, I want to do things with robotics, or hey, I have this cool idea with computer vision. They can be well-defined problem statements, or they could just be like, language models are cool. I want to make a mini ChatGPT, right? We're happy with that. And what we can offer you is ML and kind of software engineering advice and mentorship, as well as like in-person advising, which we'll go over next week during our general body meeting on Sunday, right?
Not this Sunday.
Not this Sunday. Next Sunday. More details will be announced in the Discord. So again, please join that if you have. But if you have any questions about any of these, especially interest projects, stay after. I'll happy to talk about them. But yeah, let's get started. By the way, just a fair warning-ish. Today's lecture, I'm going to be going kind of slow, like really breaking things down. If you still think I'm moving too fast, please let me know. Otherwise, today's lecture, again, since it's the intro one, we'll be going very slow. Unless anyone says anything, we will be picking up the pace in future lectures. Everyone good? Yay. Okay. Let's get started. Give me one moment. All right, just give me one moment. Just make sure everyone's connected. Okay, yeah. Let's get started. Okay, perfect. All right, let's get started for real this time. All right. So a lot of you may have seen like a lot of these terms before, right? But what do they actually mean? So let's begin with artificial intelligence, which is like the broadest definition. And so this is really anything that mimics human understanding, right? Or human behavior. Now I put surpassing, but oftentimes it's on par or slightly worse, right? And we usually define AI in the context of a subproblem, right? So you could say, hey, like in DSA, I made a AI that can solve a maze faster than a human being, right? And that could be perfectly valid, right? Some of you guys might be playing video games or something. You could call like the opposing players, like the automated player, an AI, right? And that'd be perfectly valid. So it's really just any algorithm that surpasses or is on par with, mimics human intelligence. And if it sounds vague, that's somewhat on purpose. Now, to get a little bit more specific, machine learning is a type of AI where we use data to improve performance. And data is the key word here. So without this data, our machine learning model is garbage, right? So think ChatGPT is a machine learning model, right? It kind of learned how human language works from the internet. Now, if you take out the internet portion, take out all of its data, it's just going to be spouting gibberish, right? Data is the key word here. And now deep learning is a subset of machine learning, even more specific. And again, we're still data dependent, but we use this component called a neural network. And that's the key difference. Again, ChatGPT is a deep learning model. It uses neural networks uses neurons, which form neural networks, which form bigger and bigger algorithms, right? So again, AI, extremely broad, machine learning, use data to learn, deep learning, use neurons. Everyone good with these definitions? Oh, by the way, I'm recording this and all these slides will be on the website. So I guess as nice as you want to take this. I appreciate that. I'll give you 10 seconds. All right, moving on to the next slide. Okay, so let's define what learning is, right? And again, machine learning, or just learning in the context of AI, is when our model, our algorithm, finds patterns in data and then acts on them. So in this example we have over here, so our model in orange tries to predict housing prices. Well, obviously we need data from housing prices, right? And so it looks at the data set. So think like a spreadsheet, right, or a CSV. It looks at the spreadsheet, see how the variables interact, and more importantly, how those variables interact to form the output. So it learns those trends, and then that way, when you give it new data, so like the data from my house or something, hopefully that's not online, it probably is. So it takes the data from my house and is able to predict what the house price might be. So again, the key is the model learns patterns in the data, and then we use those patterns to do whatever we want. In this case, make a prediction. Okay, so let's try to figure this out ourselves. If I were to ask you, hey, how does increasing size impact the sales price? Anyone have a guess? Notice some trends? You shout it out.
Bigger the size, the more pricey it is.
Exactly. What's your name?
John.
John. Exactly, John. Pretty straightforward, right? Yeah. So we as humans can kind of do this to a basic extent, right? Increasing size increases price. More bedrooms, more higher the price. Older houses have a little bit of lower price. And again, these are all things maybe you spent a few minutes looking at, maybe a few seconds, you could tell how they interact with the output. By the way, the output sale price in yellow. Now that way, okay, so now we've kind of found the patterns, right, in the data set. Could you now give me an estimation for how much this new house number 6, might cost? Any guesses? Just ballpark. Hans.
280,000.
Okay. Any other guesses?
300,000.
200,000. What's your name?
Joe.
Joe. 300,000. All right. 212. Close-ish, not bad. By the way, I made up that number, so I just guessed. That's my number. But yeah, so you guys kind of walk through very briefly what the model does, right? And this act of looking at the data and trying to find patterns, we call that training. The model trains itself on the data set. And then when you try to make a guess or make a prediction on new data, we call that prediction or making an inference. Both of those slightly different for our purposes, interchangeable for now. So training, inferences, those are kind of key terms. By the way, I'll be referring to machine learning algorithms, AI algorithms as models from now on. Just quick terminology. Models, training, inference, prediction. Hopefully that's not too much yet. Okay, so what are different types of learning, right? Because in machine learning, we have a lot of different subproblems. So supervised learning is one of the two big portions, subproblems. Supervised learning is what we just did. So it's when our input training data has a known output, right? So if you look at the housing prices, well, our known output would be the sales price. And the terminology for that would be a label. So the output, like the output column in our data set, in our spreadsheet, would be sales price. And again, I really want to stress that like supervised learning, like is kind of hinges on the fact that we know what the output should be. Like even with images, right? Is this a cat, right? Yes or no, like those suffice as labels, right? We know what the outputs are. So within supervised learning, we have two types. We have regression. And again, regression is what we were doing with the houses. Regression is when we try to output a continuous numerical value. Again, prices, temperature, weight, all of these are continuous numerical values. Again, you could say, hey, like my output should be negative, right? Or maybe my output could even be a whole number, right? It gets a little tricky there. But the point is like, we're predicting a number and that's the goal. Okay, now the second subproblem in supervised learning is classification. So in classification, think you're trying to predict a class or a category. So moving past the housing price data set, think about like, hey, we're trying to like predict the precipitation, rain, snow, or no precipitation. Those are 3 categories, right? 3 distinct categories. In the case of is this a cat or not? Yes or no? Well, those suffice as categories. And our model doesn't really know what the word cat is or what rain is. What it does know is numbers, right? And so what we do is we predict discrete values in place of our categories. So in the yes or no example, we could say, hey, like we map the number 0 to a no either 1 to yes. So our model outputs 0, yes or no for us. In the case of rain, snow, none, we could say like, hey, snow is 0, rain is 1, none equals 2. And our model will only output these 3 numbers. Okay. Okay, so that was all supervised learning. Classification regression, supervised learning. We know what the outputs are. When we're training, at least, when we're training. Unsupervised is we do not know the output during training. So that gets a little bit more confusing by nature. So the model kind of has to figure out what we want it to do with little instruction. So a very common example of this is clustering. So I might give the model like all of these like pictures, right, of cats and dogs. And I tell the model, hey, form groups, like just form groups of similar images. Now, I don't tell the model which ones are cats and which ones are dogs. The hope is just by saying, hey, I want 2 groups, the model can figure out, spread them out. So in this case, it grouped all the cats together and all the dogs separately. But again, I didn't tell it while training which one are cats and which ones are dogs. Okay. So quick review. Supervised learning, the key point is we know what the outputs are. And again, the outputs are called labels, right? We know what the labels are. Is it yes? Is it a no? Regression, classification are subproblems, and kind of some limitations with this is labeling is really hard, right? Like imagine you have like a data, like big machine learning models like used for like in corporations. Well, they're hundreds of thousands of lines long, right? Someone's got to annotate that, right? Like someone's got to say yes or no. And a big problem or a very common thing to do is like, how can we automate this to some degree, right? But then if you automate it and we have errors, then boom, our model has errors instantly, right? Our model is only as good as their data set in supervised learning. Again, unsupervised learning by kind of nature, it's kind of hard to define, right? Like our model has to figure out what to do with the data. Clustering is a very good example of this. It can sometimes be less interpretable, but the biggest thing is like, it's just a harder problem oftentimes. Because again, the model has to figure out what to do. Okay, brief break. Any questions so far? All right, I'm doing a good job. Okay, so yeah, given a data set, can you predict what the output should be? So in this case, at the last line of every table, there's a question mark, big question mark. And again, can you find like a mapping, or for you CS guys, a function that takes A to output, or the last one, A, B to output? All right, buzz around. Anyone know this one? What should the output be? Exactly. What's the pattern?
Where?
Perfect. Yeah. What's your name?
Home.
Ohm. Perfect. Ohm. What about for the next one? Very similar. Hans.
2048.
For the second one? Not quite. I can see where you got that though. No. Yes. To the power of. Not quite, but right direction. What's
It's 10, 24, so 2 to the power 10.
oh, wait. Not, yeah, it's cubed. No, I see where you guys got that though, for the 1024. That's totally fair. It's cubed. It's cubed. Yeah, because I was doing even numbers. I can see that. Okay, last one. Very fun. Anyone got the last one? All right, you guys got 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2. Yeah, I was expecting a lot of people to get it anyway. That was kind of the challenge one. All right, reveals. The last one was a circle. A squared plus B squared equals output. Yeah, I wasn't nice with the numbers. I was not nice with the numbers. That's kind of the point, right? Like, so in practice, right? Like, if this were to be given to you like on a test or something, right? How would you figure it out? Well, I think traditionally in math classes, you like, graph points. That's a very common one. Maybe use a calculator like linreg, quadreg. But if I were to give you the AB output data set, right? If I were to add like 10 more columns, will your strategy still work? Maybe if you had the whole day, right? We usually don't have the whole day, right? We're all very busy. So again, with machine learning, even AI in general, we want a model, right? Our AI algorithm. So to learn any data set, right? Learn the patterns from any data set and make the predictions, make the relevant predictions. So this one, I don't even remember what it was. I cooked something devious in Desmos. I'm sorry. The second one though, in practice, right? Your numbers in the real world very rarely be like clean, nice whole numbers, right? Oftentimes they'll be continuous, they'll be noisy, right? plus 0.1 here, minus 0.8 here, things like that. So anyone know the rough pattern for the second one? We've seen it before. Yep, it's cubed. It's cubed. Yeah, but that may have taken a few more seconds, right? Maybe you won't have been able to figure it out as quickly if I didn't give the hints, right? And that's kind of the point. Even with something as simple as the underlying pattern, humans are already getting outclassed. So again, the goal with machine learning, right? Can we learn any data set, learn the patterns within the data set? Okay, so let's kind of walk through our very, very first bare bones machine learning model, deep learning model to help us get there. Okay, so here's kind of the setup, the problem setup. So given weather data, can we predict the rainfall? So in this case, we have something called features. So with every line of inputs, we have categories within that inputs. So in this case, for a single days of data, or for a single day of weather data, we have humidity, temperature, wind speed. Each of these would be called features. So 3 features makes sense. And again, let's say we know, like in the real world for today, like the amount of rainfall was 36.5. Now, how do we get from this to that, right? But okay, before we move on, does anyone remember what type of problem this is? Supervised or unsupervised? Oh. And what subproblem? Classification, regression? Oh. Perfect. Hey, paying attention. I like that. Okay. So let's break this down, right? Again, we're trying to get from features to outputs. So in our current model, each feature gets a number called a weight. And the weight reflects how much the feature impacts the outputs. So just by looking at the weights, it tells us 2 things: the importance of that feature to the outputs and to the sign of that feature. As in, like, is it a positive relationship? Will increasing this feature increase the model, or will it decrease the model, a negative relationship? Okay, I'll break down weights in a little bit more. But each feature gets a weight. We multiply the feature numbers by the weights, and then we add them up. So 80 times 0.5, 25 times minus 0.2, so on. Then we add the sums. So 40 plus minus 5 plus 0.5. It's just a weighted sum. It's just a weighted sum. Any questions about the math or calculations? Okay, perfect. Okay, let's break down like kind of the conceptual a little bit more. Let's take a look at the weights for humidity and wind speed. So, okay, I changed the numbers really quickly, by the way. Everything's 1 now. So if we add 1 to humidity, like plus 1 to humidity, well, hey, the output increases by 0.5, right? If we add plus 1 to wind speed, the output only increases by 0.1, right? So just by making like the same change in one feature, our model reacts a lot differently. Or sorry, our output reacts a lot differently. So you can see humidity has a greater impact on the outputs. Does that make sense? And we could just eyeball that and figure that out just by looking at the weights. Okay, and then let's take a look at temperature. What happens if we increase temperature by 1? Well, the weight is negative, right? So the output, the rainfall, is lowered. Make sense? Importance and positive or negative relationship. Perfect. Okay, hopefully we're still going good. Okay, but question: what happens if all the inputs are 0, right? Well, it's multiplicative. Like we multiply stuff together. If one number is 0, everything's 0, right? The weighted sum's output is 0. But does that mean that the rainfall should be 0? Like, let's think of a separate problem, right? Like in that, whatever problem you have in your head, if all the inputs are 0, should that output also be 0? Not necessarily. It might be like 0.5 or 0.3. It might be like start super big, right? How do we account for this? Well, we have something called a bias. So the bias is independent of the inputs. So we add the bias, again, it's additive, not multiplicative. We add it to the weighted sum once we finish multiplying everything. So yeah, in this case, everything's 0. We add the bias, our output is 1. Hey, happy rainfall is 1, not 0. And again, you could have a bias of 0, right? But this just gives us that flexibility, right? We're not fully dependent on the input. A model can still respond when we have all 0 inputs. Okay. Now, the very last step in our very basic model is called the activation or activation function. So that just adds a oftentimes nonlinear transformation to our input. So what does that mean? In this case, we don't really need that, right? Because I've gone back to the normal numbers. Right before we get to the activation function, our rainfall is 36.5. That's a very reasonable rainfall, right? Why would we want to transform that? So activation will be a lot more important later on in this lecture, but for now, just kind of ignore it. I have the identity function, f of x equals x, just so, because again, it's still part of the pipeline, but for now, we'll not really paid too much attention for it. Okay. Okay. So this model that we've just built is called a perceptron. So just brief recap of everything. We have features, categories of the inputs, weights assess the importance and kind of direction of the relationship with each feature with the outputs. Bias, they update their additive, they update the output independence of the features. And then finally, the activation that further transforms the outputs, right? And again, we will get more into the activation later. We're going to kind of ignore it for now. Okay, we've gone through a lot of content. Any questions so far?
Here, we might have idea of the features. I'm a bit confused about this weight, like.
Yeah.
Why are we getting this weight? It's like probability or like percentage, like the humidity, something like that, or temperature, something like that. Like,
Yeah. In practice, they're just really any number, right? Like really any like a decimal, positive or negative number. And again, all they tell us is how important is that number. Now, it's not a percentage. It's just a number. Because again, our output could be like a number between 100 and 200, right? If we have percentages, that forces our numbers to be very small, right? And oftentimes, in this case, we want a big number like 36.5, maybe 100. So percentages won't work. But again, just by looking at the weights, like conceptually, they tell us bigger weight, more importance. If the weight is negative, that means the feature will decrease the output. So again, in practice, a perception is just a weighted sum plus a bias to get our output, right? In other words, like what numbers can we pick to get that 36.5, right? Does that make sense, hopefully? Okay, I'll be staying after if you guys have any deeper questions. Yeah.
So you chose the ways before that.
Exactly. Yeah.
You chose like different weights that would equal the same.
That'd be totally valid. That'd be totally valid. But yeah, you bring a what's your name? Neil. Neil brings up a very good point. I chose the weights and biases. You should not be doing that. You will never be doing that. For practice sake, I am, but next lecture we'll go over how to choose weights and biases. But you bring up a good point. Yeah, these numbers can be anything we want as long as we get the desired output, right? But yeah, good questions. Okay, so that was just regression, right? How do we apply this model to classification? Remember, let me introduce a new problem, binary classification. Outputs are either a 1 or a 0. Usually yes or no. Straightforward. In this case, let's move to will it rain or not, right? Binary, yes or no. So again, I already explained. Okay, so how can we do this, right? Because again, the weights and biases structure means that we can really get any number, right? We can maybe force ourselves to like pick weights and biases that are always like close to 0, always close to 1, but that can get very tricky very fast. There's a very, very easy solution to this. Okay, sigmoid. What? Is it about to turn off?
If you clicked it, like it's not going to do it anymore.
That happens in class all the time. Okay, sigmoid. So this is one of those activation functions we're talking about. So we have a use for it now. What sigmoid does is it maps a inputs to a number between 0 and 1. Oh, you were right. So you just turn it back on or something?
Yeah.
All right. Our lovely Alex for tech support.
This would be a good time to ask the question again.
I already asked. Great question. Traditional regression models usually one output. Oh, sorry. I misunderstood. No. For this model we're covering right now, we only have one output. Future models can have as many outputs as you want. So you could do regression on like 5 different things. Traditionally, it's only one, but there's no reason why you can't do more.
When it turns on, make sure that you're still recording it on the screen.
I am.
No, I when it turns on.
Yeah.
So you lost the line.
Is it on now?
Serious, it's warming up.
Gee, wait, it always beeps during class and it never turns off.
I've seen it turn on everything that happens.
All right. Sorry, guys. Technical difficulties. I don't know.
You're good.
All right, we're back. Yay. Okay. I'm on that. All right, recording. Here, join back and see. Okay. Sorry, guys. Thanks for your patience. Okay. Sigmoid. Yay. Sigmoid is a function, just in general, right? Let's take a break from the machine learning stuff. Maps a number and input from a 0 to a 1. That's all it does. You'll never get anything less than 0, never anything more than 1. So, for example, if you were to throw the number 2 into our sigmoid function, 1 over 1 plus e to the minus 2, the output would be 0.8, right? In the case of minus 4, well, that's closer to 0. So the more positive the number is, the closer it is to 1. The more negative, the closer it is to 0. And again, you can see that I graph the points, right? Again, like it's asymptotic towards 1 and 0, right? So if I were to ask someone, if I were to do sigmoid of 100, what would the output like roughly resemble? 1, like pretty much 1 on the dot. Like your calculator would probably say 1, 0.99999. Yeah. Okay, good. So how can we use this? Well, let's just plug this into our, sorry, give me 1 second. So I see what's going on. Okay, yeah. So we just plug this activation function right before the output. So we use the activation function now, right? So we take that minus 1.5, plug it into that activation sigmoid, or sigmoid activation, sorry, and then we get 0.182, right? That's what sigmoid gives us. Hey, remember, we want 0 or 1. So at this point, it's very easy, just round. Yeah, again, rounding is separate from sigmoid, but it's rounding, right? Very easy. Okay. Now, question: what happens if the input to sigmoid was 0.5? Again, in practice, it will never be 0.5 on the dot. Hopefully, it won't be. But this means the model is completely unsure what the output should be, right? So, just generally, the closer the inputs is to 0. Sorry, not 1. The closer the input is to -1, the less confident the prediction. No, that's not true. The closer the input is to 0, the less confident the prediction is, right? A very confident prediction would mean it's like somewhere like along here, right? You can really just think of sigmoid as like a probability in this case, because you're getting a number from 0 to 1. If sigmoid gives you 99, well, you can almost say, hey, I'm 99% sure it will rain. You good? Okay. So back to regression, going back to regression. What if we had a single feature, right? What would our model look like? By the way, I took out the sigmoid. Well, if we were just kind of format this as an equation, it would be input, it would be the single input times a single weight, because again, 1 feature per weights, or 1 weight per feature, sorry, plus a bias. That's just y equals mx plus b. That's just a line. And the point of this is that with our perceptron model, at best, we can model linear relationships, right? And so what does this like mean specifically in like a more common case, right? So let's fix all the other features. Like let's fix humidity and wind speed to be like the same inputs. And let's only fluctuate temperature. So right now, if we throw in like a temperature of 1, do all the weighted sum, do the bias, the activation, which does nothing, we get an output of 0.8. What happens if you up that to 2? Well, the output decreases to 0.6. If you up it to 3, output 0.4. You guys noticing a pattern here? It's linear, it's a line. In this case, for our line, the intercepts would be the bias plus these other weights. So plus the weighted sum from this guy and the sum from this guy, plus the bias. Again, don't worry about that too much. The important thing is the slope. The slope is just the weight, the minus 0.2, right? But again, we do this for any feature, for any perceptron model. The relationship between any feature and the output will always be linear at best. Like we can't do better. And hopefully that should be clear why, because the y equals mx plus b structure. Let's kind of break this down a little bit more. Here's like a dummy data set I made, sorry. Here it just predicted someone's an Amazon Prime member or not. Here's the average hours they spent on the site, their balance, I guess negative numbers or discounts. It's not super important. Our classes are A and B. A, I don't know, Amazon Prime, B not. Again, this is a classification problem. We're predicting A or B, binary classification. So we can graph these points And then set our y-axis as the first feature, the average hours, and the x-axis as the balance. And then we just color code what the different classes are. Okay, so you can see, hey, there's like a very clear separation between these two. Like you can almost draw some sort of line to like separate these. And the cool thing about perceptrons is we can't draw that line. Like something like this, for example. We want something like this. Can we do it with a perceptron is the question. So here's the equation that lets us draw this line. You can literally plug this into Desmos. That's what I did. And you can draw the line. I won't go to the derivation of how I got this to like right now. It's essentially if you solve for this, the stuff inside the simulated function, you'll get x1 w1 plus x, or sorry, that should be x2 w2 plus b equals 1, which is just like a linear function. Again, I'll go through this later. It's not super important to understand. What is important is this line is called a decision boundary. So again, everything above the line is class B, everything below is class A. And so this decision boundary with a single neuron, we'll get a line at best, right? And I do want to stress that we have two features. So the decision boundary is in 2D. If we have three features, imagine a plane, right? And everything above the plane is one class, everything below the plane is another class. The same concept applies for 4D, 5D, however many features you want. You just can't graph it at that point. Okay, so the big question now is how do we model these non-linear relationships? Because we could do this in like algebra 1, right? This isn't very impressive. We want to do way better than this. Okay. Quick break. Everyone clear about why perceptrons can only do linear relationships? And even if you're not clear, can you guys just accept that? Like, does that make sense? Perceptrons can only do like lines, linear relationships. Again, any questions about this? Meet me after lecture. Okay. So before we move on to the more advanced stuff, let's kind of change our representations. So everything in the dotted box, let's just cram that into like a circle, just 1 unit. Again, you can now all we see are inputs. So 3 features, 3 lines, and our output, 1 output, 1 line. You go with the representation. Again, same thing, just less fun to look at. Okay, this is a neural network. What we've been building up to. Some of you may have already heard about this. And the idea of a neural network is that we have a bunch of these gray guys, so our perceptrons, that feed into each other, right? And the hope, the goal is that by having so many of these perceptrons feed into each other, we can do a lot more than linear. I mean, it looks complicated, like it just looks complicated, right? The hope is that we can get that complexity. Like a model can learn and recognize patterns that are more than just linear. Okay, but how exactly do we do that? Let's go over some terminology. So just as before, the green is input, right? So if nothing's changed from the input side. Kind of the crux of this is the hidden layers. So everything here is a perceptron. So terminology change. When you use a perception by itself, well, it's called perceptron. But when it's a part of a neural network, it's called a neuron. Now, the guts of the neuron perceptron is still the same regardless. It just, we call it a neuron because it's a neural network. Same thing as a perceptron. But yeah, all of these guys in what we call hidden layers are neurons. And we kind of think of them in terms of layers. So we have our input layer, hidden layer 1, hidden layer 2, and then our output layer in blue. Again, that's still a neuron. Usually we handle output layers or like the output layers slightly differently. And we'll go into why in a little bit later, but that's just in case we need to transform the output to like, look like what an output should look like. Just a few rules. Data always flows forward, right? You never go backwards, right? Like if I'm at this neuron over here on the second layer, it's never going to send data behind it, right? You could almost draw arrows pointing forward. And neurons on the same layer are independent in the sense that they don't share information. And there is research that shows like, hey, like they have some impacts during training, but when I say independent, I mean they don't share information. There's no lines between these layers. So again, information flows forward, no information being shared across layers. Okay. Whoa, what's this guy? So here, it's just significantly simpler than this. All I've done is for every neuron, I've just labeled the weights and labeled the biases, right? So in this case, I have one hidden layer, so the gray guy, and then 1 output layer, right? So 3 neurons. Again, let's take a look. Let's like zoom in on this neuron over here. Well, hey, it's just a perceptron, right? Just like we were doing earlier. In this case, its inputs are, well, the actual inputs to the model. The green guy is 2 and 2. And again, same thing, weighted sum plus bias and then an activation. So I'm going to introduce a new activation function here called ReLU. And ReLU is oftentimes the go-to for activation functions within a neural network. So like sigmoid, it is a nonlinear function, and it really helps the model learn like nonlinear complex functions. So this is ReLU if we were to graph it. It's just a maximum. So if you input x, if x is negative, it sets that to 0. If x is positive, it doesn't bother like messing with x, right? So again, ReLU of -1 is 0, ReLU of -3 is 0. ReLU of 5 is 5, right? It's literally a line, but at 0, for anything negative, it just maps it to 0. Okay, so there are a lot of different ways you can think of ReLU. My thing, coming from a little bit of signal processing background, is like it turns off negative signals, right? So if at this point in your model, like right before going to activation, we call that a pre-activation. So right before your activation, if your input is negative, it turns that off, it silences it, right? And that's a really fun and really, really important thing of ReLU that we'll dissect later in the semester. But again, hopefully you guys can see how it's nonlinear. Like this part is fully linear, right? But just by mapping stuff to 0, it becomes nonlinear for negatives. Okay, so that was the first neuron layer 1. The second layer, neuron layer 2, exact same thing, just different weights, different biases, right? The inner guts of each neuron are like completely independent of each other. So I just want to focus on the output layer as well, because here I chose sigmoid for my activation, right, instead of ReLU. And again, that goes back to our original purpose of using an activation function, which is to get an output that like looks good per se. So in this case, hey, we're doing binary classification. Well, I can't really have minus 0.75 as an output. That wouldn't really make sense. Is that a yes? Is that a no? I don't know. So we use sigmoid to map that between 0 and 1, just like we did in a perceptron. And again, this 0.32 acts as a probability. It tells us, hey, we're 32% confident that it's a yes. Okay, and again, we get 0.32 as our final output. We could then like round separately to get a 0. And this was just an example for binary classification. Okay, a lot of stuff just covered. Any questions? Sure. Okay, I'll take that. Let's keep moving. So let's revisit that Amazon Prime example, right? Can we now draw a more complex decision boundary? We can. We can. We now have a little point there. Yeah, it's not just a line. It's 2 lines that are joining out of the point. And so the key change was this activation function we just put, that ReLU that was in our hidden layers. So what happens if we try to remove that? So by the way, the Desmos is on the slides. You guys can just click on the link if you want to play with it. Don't worry too much with the variables. You can notice that like, hey, I have a weight here, I have a bias here. X and Y are my inputs. Don't worry about that too much. The fun part is playing with the weights, right? So I think this is the weights for the first neuron that we went through. If I play around with it, whoa, it does some very, very cool, wacky things. Let's take a look at the bias. Well, it moves it up and down, kind of similar to like, if you guys have taken like algebra 2 maybe, you might know that like adding a term or like the b and y equals mx plus b, well, that translates stuff, right? So it's translating the line up and down. So that's standard. And again, like, by the way, when you guys make a neural network, you will never be doing this. Like, you will not open Desmos. This was very painful to do, even with just like a few weights. But the point is, like, we can learn like a lot of different like kind of parabolic functions with this, right? Anything that resembles like a parabola, like x squared, like we could probably fit it with this model, right? Just choose the weights and biases correctly, and then we can adapt to really anything that is roughly a parabola, right? Okay. Again, this is on the slides if you guys want to play with it. Okay. So yeah, what happens though? Oh, sorry. Let me go back. Sorry, give me 1 second. Okay. Yeah. What happens if we, okay, that did nothing. What happens if we take out that ReLU? So here's where I control the ReLU. What happens if I just make it go to X? Wait, we're back at a line. That's very interesting. Again, we still have the same number of neurons in our desmos, right? Everything else is the same. I still have the sigmoid in there. The only difference is I've taken that nonlinear activation function from the hidden layers. And we're back at essentially, effectively, a perceptron. Only linear relationships, right? So what I'm trying to get at here, what I'm trying to get at here, by the way, here is the math that shows like why by removing the ReLU that we go back to perceptron. It's not, if you want, I can dissect this later. The point is, what lets our neural networks model these complex relationships are those nonlinear activations, not necessarily at the output layer, but in the hidden layer. Just by having those ReLUs there, we get that parabola shape, right? Taking those out, we go back to our perceptron. So now this is like a little bit more of a deep dive on activations from earlier. Activations kind of have two purposes, right? The way we use ReLU was to introduce nonlinearity. And again, that's so our model can learn complex functions that aren't linear. And ReLU is just one activation function, right? If I wanted to, I could have chucked sigmoid in there in place of ReLU. Or there's a plethora. TNH is a very common one. Leaky ReLU has shown a lot of success recently. Not recently. Recently, in the last 10 years. And so you might ask, okay, how do I choose an activation function? There's a lot of research in like defining that ahead of time. For our purposes, just try them all. Just pick the one that works the best for you. In a future lecture, we'll do a little bit of deeper dive of like certain activations cause different problems. So ReLU can cause something called an exploding gradient, and it's as scary as it sounds. TNH and sigmoid can cause something called a vanishing gradient. Both are very annoying to deal with. But for our purposes, just try them. See which one works best for your problem. So that's to introduce nonlinearity. The other purpose is to transform the value at the output layer. And that's how we've been using sigmoid up until now. It's just so we can get that number between 0 and 1, right? For example, you could use ReLU to do this. Like, hey, like I only want a positive number, right? ReLU could do that for you. Sigmoid, just a very common one for classification. Okay. Now let's just for funsies, see how our model behaves when we have 5 neurons, right? So this is the neuron example. If we were to look at this guy, imagine another 2 gray, like imagine another layer, right? Just another 2 neurons. Okay, I gave up trying to fit this guy, by the way. Oh my God, like I have no idea what's going on, but it's behaving in some very cool, interesting, wacky ways, right? And so you can imagine that this model could learn more than just parabolas, right? Like over here, like, hey, I have like a corner here and a corner there. Parabola doesn't do that, right? And again, just by adding another layer of 2 neurons, we already have this like really, really interesting, like all these possibilities for functions. Oh, look at that guy that a model can learn, right? So again, but I kind of posed you a question, right? As you can see, I had no idea what I was doing. I was just playing around with the weights and the biases. The thing was going nuts. So by making our model deeper, when I say deeper, I mean more neurons, right? More layers. By making it deeper, we make the model more complex. But does it have to be that complex? Like, this is just a problem, right? Do I need this weird, funky looking guy? Like, you can probably believe that this can learn a problem. We just choose the weights and biases for it to learn a problem. But, it's a lot trickier to do that. The other thing is we kind of lose everything in interpretability, right? Before, when we were going over perceptron, I could point out a weight and you could tell me, hey, like the weight for this guy means that this feature is this important. If I were to point to a weight now in our neural network, how does that relate to our original features, right? Like, how does this weight over here, minus 0.25, that's in our output neuron, what does that weight tell us about our inputs? And again, there's a lot of research that's been going into that. But again, the deeper your model, the less interpretable it is. So it's a trade-off, right? You can do more complex things, harder to work with. And that's the theme that'll be reoccurring for future lecture. But yeah. Okay. So last stretch here, maybe another 5-10 minutes. How can we do multi-class classification? We can now do that with neural networks. For perceptron, we can do yes or no binary classification. With a neural network, we can have more than just one output neuron, right? We can have a whole output layer with a bunch of stuff. And so quick terminology dump. The output for each layer is called, the output from each output neuron, so one of these blue guys, is called a logit, right? And the higher that logit is, the more confident that the model thinks a certain class is true. So let's go through an example. We're back to, by the way, we're back to snow, rain, or none, right? We're trying to classify, trying to pick one of these classes, right? So in this case, here are logits, right? Again, this is just the numbers that we have before activation, right? Yeah, so the logit for snow would be 3, and then 1 minus 1. And again, just in case you guys don't get too confused, the logit in this case, like for a single perceptron, would be this minus 0.75. So it's the number that we have before activation. Everyone good on logits? Okay, just try not to bombard you guys with too much terminology on the first lecture. The rest of the semester for that. Okay, so we have these numbers, and now we have a very interesting activation function called a softmax. So up until now, all of our activation functions take one number as input, right? The softmax takes as many numbers as you want as input. And so for each number you input into the softmax, the output is the same, is a similar probability that we got from the softmax. So in this case, the probability of it snowing, that it's snowing is like 86%, right? 0.867. And you'll notice that all of these guys add up to 1, right? Again, the softmax for each number, for each logit, gives us a number between 0 and 1. And again, the exponential here makes it a little bit confusing, but if you really just ignore that, right? This is just a percentage, right? Like, this is really just, again, if you ignore the exponentials, this is just the logit for like one neuron, one output neuron, divided by the sum of all the other logits. So in the case of snow, it'd be 3 divided by like 3 plus 1. Plus 1 again. You might notice, okay, so why do we take these e's, right? This is a little bit more of a thorough explanation that I'm happy to give after the lecture. One quick thing, though, is that it makes everything positive, right? How would we handle this minus 1 if it was just a percentage? It'd be kind of funny. By taking it to the eth power, it kind of handles that, right? But yeah, okay, we're not quite done yet because again, we still want to know which class we have, right? We still want to output 0, 1, or 2 for classification. So then we do something called an argmax. Very fancy name. We just pick the number that gave us the biggest number. Or index. We pick the index. So in this case, the logit for snow, so the first output neuron gave us the biggest number, 0.867. Argmax sees that and then says, hey, our output is class 0. So more formally, return the argument that maximizes the function. So the function would be softmax. The arguments would be the logits, or in other terms, activations. So, okay. Everyone clear on this? I know I've been spouting activations, a lot of terminology here. Is everyone cool with logits, softmax, argmax, all those guys? Okay, perfect. Okay, that's pretty much it. Quick review. So a neuron, for n inputs, so each inputs, like in our, think we have a spreadsheet, right? Each line on that spreadsheet, we feed into our neural network. Now, each category for each of those inputs is called a feature. So again, in this case, humidity, temperature, wind speed, those are all features for this single line of inputs. Now, to get that output for a given neuron, each feature is multiplied by weights. We then sum all of those outputs and then add a bias, right? And again, a perceptron is a model that is just a single neuron, right? You wouldn't call a once we have like neural networks, that's a neuron. This guy's a perceptron. Same thing, right? Literally the same thing, just different thing to call it. Perceptrons, I really want to stress, can only learn linear relationships. It's only by stacking these guys together and having those nonlinear activation functions that we can learn really complex things. And I think that's really cool and really fun, right? No, just me. Again, regression classification, I think we're solid on that, so I won't harp on it too much. But yeah, as I think Neil said earlier, right? I've been giving you guys the weights and biases. That will never happen. You guys should not be messing around in Desmos. How do we pick them? That will be next lecture, right? We'll go through we'll do a quick review of how we get our outputs, but we'll really be focused on how do we get these weights and biases. Yeah, again, thanks for coming, everyone. That was the end of first lecture. As always, I really want to make sure you guys know. Wait, two more things. Don't leave quite yet. All these slides are on the website. The website's in the Discord or in the email you guys got recently. If you can't find, just let me know. We have one more thing. For the first 3 lectures, we have a Google Colab notebook, kind of a interactive coding project that goes along with the first 3 lectures. So Vineth has been working very hard on that.
Yeah, so as you guys are gonna come to more lectures and learn some more, talks about how to, code your first neural network. Create this interactive activity that you guys can use to plug and play with the neural network model to learn how to model a function, right? And so, yeah, you might, depending on how far ahead you guys are on lectures and whether you guys want to get more hands-on activities, this is something that you guys should definitely check out. I don't want to, put this on you guys like right now, obviously. So come to more lectures. We'll look at more interactive examples in class and whatnot. But over time, you will be able to, write your first neural network that predicts and can map out a function. So if you guys want to get a head start on that, the Google Colab is linked over there. Feel free to check it out now if you guys just want to get a head start on it. Otherwise, don't worry. Yeah.
I don't think the link is on the slide. I know, just like updated or.
Oh yeah, we'll fix that.
Yeah.
Thanks for noticing that. Yeah. Again, we'll email it to you guys and then put it in the Discord if you're on the.
And we'll bring this up more formally in like future lectures.
Yeah. So again, we didn't go over code, right? That'll be lecture 3. This is just if you want to work on it ahead of time. Myself and the website team are making a leaderboard for this. So we're gonna make it into a mini challenge. We'll be displaying the highest scores. More on this later. See you guys. Thanks, guys.